In question 4 we have a cylinder with a gas-type piston containing an ideal gas at a constant temperature of 290 Kelvin. The pressure inside the cylinder is 20 times 10 to the 4 pascals with a volume of 0.5 times 10 to the minus 3 cubic meters. In A, we need to plot 2 or 3 additional points to draw a graph on these axes to show the relationship between pressure and volume as the piston is slowly pulled out, with the temperature of the gas remaining constant. Well, as we double the volume, we'll halve the pressure. So at the moment we have a volume of 0.5 times 10 to the minus 3 cubic meters and a pressure of 20 times 10 to the 4 pascals. Doubling the volume to 1 times 10 to the minus 3 cubic meters will give a pressure of 10 times 10 to the 4 pascals. Doubling from 1 to 2, we'll go down to 5 times 10 to the 4 pascals. Doubling from 2 to 4, we'll go to 2.5 times 10 to the 4 pascals. We can then join these with a smooth curve. In B part 1 we need to find the number of gas molecules in the cylinder. Well, for this we can use pressure times volume is equal to number of molecules times the Boltzmann constant times the Kelvin temperature. Rearranging for number and putting in the values, I've taken the values given in the question. I could have taken any values from the graph. Gives 2.50 times 10 to the 22 molecules. In part 2 we need to find the total kinetic energy of the gas molecules. Well, the kinetic energy of a gas molecule is given by 3 kT over 2. We have n gas molecules. Putting in all the values, the Boltzmann constant is given on the formula sheet, gives an energy of 150 joules. In C we need to state 4 assumptions made in the molecular kinetic theory model of an ideal gas. Well, the assumptions are no forces exist between particles except during collisions. The volume of the particles is negligible compared to the volume of the container therein. Collisions between particles and between particles in the container are perfectly elastic. Also, the time particles are in contact during a collision is negligible.